like clouds and the surface. And the project that I'm working on, PolarRes, is just starting, but we're going to be using some of these sorts of techniques to investigate those processes and hopefully bring that range to make it a little bit more narrower. So if you remember that story I told you at the beginning from Larsen C, that was this little pink bit on the map. And this is the reason that I was here, really. So these satellite images show you, over the course of about 6 weeks or so, the complete collapse of the Larsen B ice shelf in 2002. So this ice shelf took lots of scientists by surprise by collapsing and disintegrating entirely fairly rapidly. And before that, in 1995, its neighbor, Larsen A, had collapsed. So we can see that there's this kind of southward progression of collapsing ice shelves, with Larsen A in 1995, the furthest north, then Larsen B a little bit further south, and then potentially, who knows, maybe Larsen C in future. So this is something that we really need to, an area that we really need to look into if we want to be better able to predict these sorts of events. A brief foray into what an ice shelf is. So on this map in the corner, you can see these kind of gray-blue areas, and those are all ice shelves. And ice shelves are like floating platforms of ice that fringe the entire Antarctic continent. They're kind of like the tongues of glaciers, which are formed when ice flowing off the continent meets the ocean, spreads out, and forms this floating platform. Now, within that ice shelf, you have, at the very bottom, pretty much solid ice. At the top, you have lovely fresh snow, which has loads and loads of air pockets in it. And in the middle, you've got this layer called firn, which is a kind of intermediate, somewhere in between product between snow and ice. And as you go through the down through the ice shelf, it gets much, much denser. And this is really important because those air pockets at the surface can kind of soak up meltwater that collects at the surface. So every summer you get melting, meltwater trickles into the ice shelf, it stays in those air pockets, freezes, and solidifies. And that's how you get this increasing density with depth. Usually, the rate of snowfall is balanced by the rate of kind of densification. That's fine, that's a stable state. But increasingly, that doesn't happen. And more of the ice shelf is becoming solid ice. So it's getting completely saturated with meltwater that then freezes, turns into a complete solid lump. So this can cause a process called hydrofracturing. And this is what is responsible for the loss of Larsen A and Larsen B. And hydrofracturing is literally just cracking by water. So when you've got a solid ice block of an ice shelf, when there are existing cracks and crevasses, any melt that happens at the surface can just trickle in, fill up those rifts, fill up those crevasses. And as it starts to fill up those crevasses, once it gets to this magic 90%, the weight and pressure of that water is so great that it completely propagates straight to the bottom of the ice shelf. All over the ice shelf this is happening, and the thing disintegrates into smithereens like you would have seen in those satellite images. And this process is driven almost exclusively on the Antarctic Peninsula by surface melting. And this is what it can look like in real life. This is a photo taken by a Basque colleague as they were flying over another ice shelf on the Antarctic Peninsula. And we really care about surface melting because those ice shelves act like a plug or a cork. So when you remove an ice shelf, all the glaciers that flow into it are able to flow unrestricted into the ocean. And although the ice shelf itself is already displacing its own weight in water, it doesn't contribute to sea level rise when it collapses. The glaciers that it holds back, when they start flowing into the ocean, that does contribute to sea level rise. So this is an indirect influence on global sea levels. I've been involved in some work by a colleague in Sheffield, Pete Tuckett, and his work has been looking with satellites at how much meltwater collects on the surface of ice shelves in Antarctica. And this plot in the central panel, which shows you the whole continent of Antarctica with red colors, shows you the kind of amount of surface melt that collects over Antarctic ice shelves. And then the little panels around the edges are zoomed in kind of individual ice shelves that show you the frequency of how often melting happens over specific ice shelves. So you're seeing the same sort of patterns happening every single year, which collects in the same places with the same sort of spatial patterns, which can potentially drive future collapses. And ice shelves across Antarctica are vulnerable to this process. So this is from a piece of work that I did a couple of years ago, projecting out into the future, again, using a regional climate model. And what we found was that at various different levels of warming, several ice shelves were particularly vulnerable to this kind of process. So some ice shelves tend to be very structurally resilient, purely because of geography or the way they are. So, for instance, this George VI ice shelf is squished in on all sides by rocks and land. So even if it melts really extensively, and in fact that picture from a couple of slides ago was over George VI, even if it melts very extensively, it's not likely to collapse because it's structurally very resilient. However, there are 4 ice shelves that we identified that at 4 degrees worth of warming particularly, but also at 2, are especially vulnerable to this kind of surface-driven collapse, including Larsen C. So this is a consistent finding, as you'll see, throughout a few different methods. So on the one hand, the kind of satellite method from Pete Tuckett, modeling, looking out into the future. And then again, this is another piece of work that I've been involved with, which uses a completely independent method, which is an atmospheric way of thinking about the same thing. So rather than thinking about melt itself and simulating melt itself, we're thinking about what sort of temperatures might trigger the level of melting that would be required to trigger a collapse. So if you're interested, it's this atmospheric metric that tells you about the kind of the intensity of melt potential, which is calculated from probability distributions, which I've attempted to draw here very badly. But essentially what I'm trying to say is that the same ice shelves stand out using this method as with this one. You see the hottest, reddest, pinkest colors identify the places with the most risk or the hot spots for melting. And to predict that future of ice shelves, we really need to understand what is driving that melting, what's driving that temperature to reach the level that it's going to trigger melt. And this is from some work which I did in very, very fine detail, looking exclusively at the Larsen C ice shelf. So if you're interested, this is in 2 papers that came out this year. And we zoomed in over the Larsen C ice shelf to figure out basically what's causing, when we get huge amounts of melting in the summer, for instance, why is that? One of the primary ones, if we think about summer, when 90% of the melting is happening, you get really sunny conditions, that causes melting. You get cloudy conditions when they're very, very thin clouds. You can still get lots of solar radiation reaching the surface. That drives lots of melting too. You can also get these very warm, dry winds that come over the mountains. They also drive lots of melting. And you can get the combination of all of these 3 as well, which can add and enhance the amount of melt that we see. In the winter, you have to have a combination, a very, very specific, very special combination of all of these things together to actually produce any kind of melt, because in winter it's minus 25 over this ice shelf. It's completely pitch black. You're not going to get any solar radiation. And then finally, in the shoulder seasons around the edges, clouds become really, really important. And this is something that we found that was fairly intriguing. That clouds are likely to become much more important as temperatures rise, because the temperatures during cloudy conditions hover around -1 degree. We know that the Antarctic Peninsula is warming very rapidly. It's likely to reach 0 degrees very soon. And at that threshold, which is the melt threshold, it's likely that these sort of cloudy conditions are going to become much more, conducive to melting. And we're going to see a Larsen C that looks a lot more like Greenland. And finally, this is a piece of work done by a colleague at Liège, thinking about how clouds are likely to impact future melt rates again. So clouds are currently the largest source of uncertainty in our future climate projections. Particularly, clouds can enhance melt via this melt albedo feedback. So BMO spoke about albedo, the reflectivity of a surface. So a bright white surface is very much like a mirror. It reflects a huge amount of incoming radiation back to space, keeps the surface relatively cool. But when you get clouds, it can trigger melting, and it starts to form these ponds like we saw in those satellite images, and those ponds are much darker than the surrounding white surface, so it absorbs more energy, and that produces much larger ponds, and it is a reinforcing loop. So you get more and more melting, and then when the clouds are gone, even the sun's energy can continue to do the melting. And this work by my colleague was looking at the kind of relationship between temperature and melt over time. And in Antarctica, you can see this relationship, all the different colors, different models again, all of them agree fairly closely, and there's a very narrow range when it comes to melt v temperature. But when we think about how much melt happens over time, there's a much larger range between models, partly because models have different temperatures that they think are going to be realized by the end of the century, but also very strongly because they all have different ideas about what clouds are going to do. And clouds are actually the largest driver of that big range of difference on the right-hand side. And that's mostly because those clouds have a strong relationship with infrared or long wave energy, which causes melting via this melt albedo feedback. This is just, there's lots of measurements going on, particularly at the British Antarctic Survey. We do a lot of work studying clouds and trying to collect observations. They're really notoriously difficult to observe directly. You have to fly through them. You have to go to Antarctica to fly through them. You can remote sense them by putting your instruments on the ground. And getting an overall picture of what clouds are doing is of paramount importance to reducing that range, that uncertainty in our climate observations, but also to understanding how the processes interact. So this is another project that's going on at the British Antarctic Survey that is aiming to do exactly that. And I just wanted to kind of end on why this matters. So ice shelves are very important. You know, they're these gatekeepers to future sea level rise. For example, we're seeing this ice shelf that is restraining the Thwaites Glacier in West Antarctica, which is down here on that little map you can see. And there's some signs that this ice shelf, which restrains that Thwaites Glacier, is starting to destabilize. And some research that came out last year suggests it could even collapse within a decade. And that would accelerate the already extremely high ice loss from this vitally important glacier in the West Antarctic region. And, you know, the loss of the Thwaites Glacier could be this trigger for entire West Antarctic ice sheet collapse, which could be potentially 3+ meters of sea level rise. So understanding the sort of processes and how ice shelf melting and loss in this important region has very, very real global implications. Although I should say that it's mostly not surface driven in Thwaites. So just finish with some take-home messages. I think the loss of ice shelves is super important when we're talking about sea level. It's often not necessarily thought about because the ice sheet is what directly contributes to sea level rise, but ice shelves can act as these kind of gatekeepers to that. They're vulnerable from melting from above and below. They're in this like melt sandwich. You get the ocean warming, get the atmosphere warming, and they're getting thin from both sides. And particularly on the Antarctic Peninsula, surface-driven hydrofracturing is very, very important. And regional climate modeling can be a really powerful way to explore these sorts of things in the future and also in the present when we have fairly limited observations. So thank you very much for listening. And if you have any questions, happy to answer them.
Yeah, hi. Thanks for a very nice talk. I'm just wondering on what timescales do these hydrofractures actually take place?
That's a two-layer answer, I think. So the actual collapse itself would take, in the case of Larsen B, it was the first satellite image was January 31st, and the second was, the last one was like 4th of April. So it's, you know, really quick, 6 weeks, 8 weeks, something like that. But what you need for that to happen is for it to have been kind of primed beforehand. So you need to have those successive years where the ice shelf is getting solidified. It's turning into solid ice. The snowfall is not replenishing it. So you have to have this imbalance for a long time. And, we think that that was happening for a while in Larsen C because temperatures were rising so much. That seemed to have kind of slowed down a little bit now. But as the climate continues to warm, it's very likely to resume that trend. So two answers, I guess. It takes a long time, but the actual collapse itself is much shorter.
Good afternoon to everyone. I'm called Fongo Eric from Cameroon. I just want to ask a question that concerning loss and damage, especially in the temperate and polar region. Now, with the increase in temperature, what are some of the strategies that your institutions have put in place to reduce the thawing or the melting of the ice that can cause more damages? Thank you.
Great question, and very, very important, because obviously the cryosphere is ultimately so impactful to all of our lives, particularly those of us who are dependent upon it for water resources or live near coasts, which could be inundated with more sea level rise. So our institute, I mean, the primary way of avoiding those loss and damages has to be first and foremost reducing emissions in the first place. And, our institution is sending people like me to COP as to participate. There's following on from that. I mean, once you've done your as much mitigation as you can, then you have to start talking about how to adapt to those changes. And I think scientific research is so important with that, because if you don't know what you're going to have to adapt to, then there's no way to kind of actually do the adaptation. So this sort of research, this sort of forward thinking regional modeling, which is much more detailed and has much more kind of relevance to people's lives, like it's one thing saying, oh, the world is going to warm by 1.5 degrees or 2 degrees, but what that actually means for you and the place that you live, for me and the place that I live, that's much more important. So things like this sort of storylines approach or the impacts focused approach is, for me, I think, a really exciting way to change the sort of journey of scientific research. So yeah, that's one of the ways that we're doing that. Happy to talk afterwards as well. I'll leave that to you.